Hello everyone. The subject is EC3501 Wireless Communication, third unit Modulation Techniques and Equalization and Diversity. The topic is Linear Modulation Techniques. These are the topics in the third unit. Let's start with Linear Modulation Techniques. The digital modulation is classified into two types. One is linear modulation and second one is non-linear modulation. In the case of linear modulation, the amplitude of the transmitted signal varies linearly with the modulating digital signal. They usually do not have constant envelope. They are more bandwidth efficient and spectral efficient. There are several examples for linear modulation techniques. Some are QPSK, OQPSK, pi by 4 QPSK. These are some of the examples of linear modulation techniques. And the second one is non-linear modulation. They may have either linear or constant envelope. Some examples of linear modulation techniques are binary phase shift keying, differential phase shift keying, quadrature phase shift keying, offset quadrature phase shift keying, and pi by 4 shifted quadrature phase shift keying. Let's see the modulation techniques one by one. First one is BPSK, that is binary phase shift keying. It is the digital modulation scheme that conveys data by changing or modulating two different phases of a reference signal, that is the carrier signal. So these are the waveforms. The first one, it is the digital data, and the third one, it is the carrier wave, and the last wave, it indicates the phase shift keying signal. And the second example is the differential phase shift keying DPSK. It is a common form of modulation, phase modulation, that conveys data by changing the phase of the carrier wave. The phase of the modulated signal is shifted relative to the previous signal element. The waveform is also shown. And next type is quadrature phase shift keying, that is QPSK. It is a form of PSK signal in which two bits are modulated at once, selecting one of four possible carrier phase shifts. They are 0, 90 degrees, 180 degrees and 270 degrees. And the next one is offset quadrature phase shift keying. It is a variant of QPSK modulation scheme where the phase or timing of either the in-phase or quadrature component is shifted relative to each other by a 1-bit period or half a symbol period denoted by TS when compared to QPSK. This is OQPSK, that is offset quadrature phase shift keying. And then we have the pi by 4 shifted quadrature phase shift keying, that is pi by 4 QPSK. It is pi by 4 shifted version of QPSK referred as pi by 4 QPSK. This modulation compromises between QPSK and OQPSK, and the maximum phase transition is about 135 degrees. And let's see the examples of constant envelope modulation, that is binary frequency shift keying BFSK, minimum shift keying MSK, and Gaussian minimum shift keying GMSK. The first one is binary phase shift frequency shift keying. It is a modulation technique in which the frequency of the carrier signal varies according to the digital signal changes. So here we have two carrier signal, one is high frequency carrier and another one is low frequency carrier, and the final output is the FSK signal, that is binary frequency shift keying signal. Let's see the combined linear and constant envelope modulation. One is M-array phase shift keying MPSK, and second one is M-array quadrature amplitude modulation QAM, and the third one is M-array frequency shift keying MFSK. So in our syllabus we have two topics, that is MSK and QPSK. Let's see MSK first. MSK is nothing but minimum shift keying. Minimum shift keying is a special type of continuous phase frequency shift keying, that is CPFSK. The peak frequency deviation is equal to 1 by 4th the bit rate. Or in other words, MSK is continuous phase frequency shift keying with modulation index of 0.5. We know about modulation index. The modulation index of FSK is similar to FM modulation index. It is denoted by KFSK. It is defined as 2 del F by RB. Del F is nothing but peak RF frequency deviation and RB is the bit rate. So modulation index of 0.5, it corresponds to the minimum frequency shaping that allows two FSK signals to be coherently orthogonal. The name minimum shift keying implies the minimum frequency separation, that is the bandwidth that allows orthogonal detection. So let's say the condition for orthogonality. Two FSK signals are orthogonal if the following condition is satisfied. That is integral 0 to t. The two signals are VH of t and VL of t. The product of VH of t, VL of t over the integral 0 to t, it must be equal to 0. This is a condition for orthogonality. So MFK is also referred as fast FSK, as the frequency spacing used is only half as much as that used in conventional non-coherent FSK. And an important feature of MSK is it is spectrally efficient modulation method. So it is used in mobile radio communication system. Some properties of MSK are also mentioned. They have constant envelope and they are spectrally efficient, and the bit error rate performance is good for MSK, and it has the self-synchronizing capability. These are the important properties of minimum shift keying technique. So MSK, it is a special form of OQPSK. OQPSK is nothing but offset QPSK, where the baseband rectangular pulses are replaced with half sinusoidal pulses. Let's see the definition of MSK signal. The MSK signal can be represented in mathematical expression. It is given by this equation. Here Mi of t and Mq of t indicates the odd and even bits of bipolar data stream. This is the representation of MSK signal. And the same MSK equation can be rewritten using trigonometric identities, that is cosine form. It can be written in cosine form. It is nothing but root of 2EB by TB cos 2 pi FCT minus Mi of t, Mq of t, pi t by 2 TB plus pi k. Here pi k, it indicates the phase. It is 0 or pi depending on whether Mi of t is 1 or minus 1. So let's see the power spectrum of MSK. The R of power spectrum is obtained by frequency shifting the magnitude squared of the Fourier transform of the baseband pulse shaping function. The baseband pulse shaping function is given by this equation. P of t, it is equal to cos pi t by 2t. So the normalized power spectral density for MSK is given by the second equation. It is nothing but the frequency shifting the magnitude squared of Fourier transform of the pulse shaping function. We have taken the Fourier transform after frequency shifting the pulse shaping function. So this figure indicates the power spectral density of MSK. Here the power spectral density of MSK is compared with QPSK method as well as OQPSK method. The waveform, the figure, it shows that MSK spectrum has lower sidebands. Here in the figure, the continuous line, it indicates MSK power spectral density, and the dotted lines, it indicates the QPSK and OQPSK power spectral density. So when compared to QPSK and OQPSK, the MSK spectrum has lower sidebands, and 99% of power is available in bandwidth 1.2 by T, and the roll-off rate is fast, and main lobe is very wide in the case of MSK, and the figure shows that it is less spectrally efficient. So this is the MSK transmitter. This is the block diagram of MSK transmitter. Let's see the explanation for this block diagram. So here the carrier signal is multiplied with cos pi t by 2t, produces two-phase coherent signal, one at Fc plus 1 by 4t and Fc minus 1 by 4t. You can see this in the block diagram. And these two FSK signals are separated using two narrowband bandpass filters, and they are approximately combined to form the in-phase and quadrature carrier components x of t and y of t respectively. These two carrier components are multiplied with odd and even bit streams. So we know odd bit streams are denoted by mi of t and even bit streams are denoted by mq of t. And they are multiplied to produce the MSK modulated signal. The MSK modulated signal is denoted by SMSK of t. So this is the MSK receiver. This block diagram indicates the MSK receiver. Here we have multiplier, integrators, then we have the switch, and finally we have the threshold device. So the received signal is multiplied by the respective in-phase and quadrature carriers x of t and y of t. The output of the multipliers are then integrated over 2-bit periods and dumped to decision circuit at the end of each 2-bit periods. Based on the level of the signal at the output of the integrator, the threshold detector decides whether the signal is 0 or a 1. The output of the data streams corresponds to mi of t and mq of t, which are offset combined to obtain the demodulated signal. So this is about MSK, and the second one is GMSK, that is Gaussian minimum shift keying. So Gaussian minimum shift keying, it is a simple modulation scheme. It is a derivative of MSK. Here the side lobe levels of the spectrum are reduced by passing the modulating NRZ data waveform through a pre-modulation Gaussian pulse shaping filter. So here we are using one Gaussian pulse shaping filter. Let's see the function of Gaussian pulse shaping filter. It smooths the phase of the MSK signal. It stabilizes the instantaneous frequency variation over time. It has the effect of considerably reducing the side lobe levels in the transmitted spectrum. So let's see, in addition to that, the pre-modulation Gaussian filtering process has the following functions. First one is it converts the full response message signal into a partial freq response scheme where each transmitted symbol spans several bit periods. Since pulse shaping does not cause the pattern averaged phase to deviate from that of simple MSK, GMSK can be coherently detected just as MSK signal or non-coherently detected as simple FSK. So GMSK is most attractive for its excellent power efficiency and spectral efficiency. The pre-modulation Gaussian filtering, it introduced ISI. ISI is nothing but intersimple interference in the transmitted signal. But the degradation is not severe if the 3 dB bandwidth bit duration product BT of the filter is greater than 0.5. So these expressions indicates the first one, it indicates the impulse response of the pre-modulation filter. It is denoted by Hg of t. And then the transfer function of the same filter is given. It is denoted by capital Hg of f. And here the parameter we have alpha. Alpha is related to the bandwidth b by the third equation, that is alpha is equal to root of ln 2 divided by root 2 into b. It is nothing but 0.5887 divided by b. So the GMSK filter may be completely defined from two parameters. One is b, that is 3 dB baseband bandwidth, and second parameter is t, baseband simple duration. This figure, it indicates the power spectrum of GMSK signal. So the power spectrum of MSK and GMSK are more or less equivalent when the BT product is infinity. As BT product decreases, the side lobe level falls off very rapidly. If BT is 0.5 for GMSK, the peak of side lobe is more than 30 dB below the main lobe, and for MSK, the peak of the side lobe is only 20 dB below the main lobe. So this is represented in the power spectral density diagram. So mobile radio channels induce an irreducible error rate due to mobile velocity. So as long as the GMSK error rate is less than that produced by the mobile channel, there is no penalty in using GMSK method. So bit error rate is another parameter. The bit error probability is a function of BT, that is bandwidth symbol duration product, since the pulse shaping impacts the intersymbol interference. The bit error rate probability of GMSK is given by this equation. Here gamma is equal to 0.68 for GMSK with BT 0.25 and it is 0.85 for simple MSK. Simple MSK has BT, it is equal to infinity. And this is a GMSK transmitter. So GMSK signal is generated by passing NRZ message bit stream through a Gaussian baseband filter. It is followed by an FM modulator or FM transmitter. So this GMSK technique is used in US cellular digital packet radio as well as in global system for mobile systems. So this is the GMSK receiver. This is a block diagram of GMSK receiver. So in the case of GMSK receiver, it is also called as GMSK detector. So GMSK signal can be detected using orthogonal coherent detectors or simple non-coherent detectors such as standard FM discriminators. Carrier recovery is performed by a method where the sum of two discrete frequency components contained at the output of the frequency doubler is divided by 4. This type of receiver can also be implemented using digital logic. So this is a digital logic circuit for the GMSK demodulator. So here we have the logic gates, flip-flops, clock recovery circuits are available. VCO, it is voltage controlled oscillator. And then we have the loop filter. So in the case of GMSK receiver, we have two deep flip-flops. They act as a quadrature product demodulator and the XR gates act as baseband multipliers. And the mutually orthogonal reference circuits are generated using two D flip-flops. VCO is voltage controlled oscillator. The center frequency is set equal to 4 times the carrier center frequency. An non-optimum but highly effective method of detecting GMSK signal is to simply sample the output of an FM demodulator. So this is taken from the textbook Wireless Communication by Rappaport. Thank you.